This work describes a mechanical approach of using high gravity to decrease the capillary length and increase the spreading rate of liquid puddles on wetting flexible substrates. There are three main regimes of spreading. The focus of this work is on two of these regimes: surface tension and gravity-driven spreading with at least micron scale thicknesses. In surface tension-driven spreading, the radius of the puddles is less than the capillary length. In gravity-driven spreading, the radius is much greater than the capillary length. In these two regimes of spreading, the droplet's area and thickness have unique power scaling with respect to time described by Tanner's law with an exponent of -1/5 for the decreasing thickness, and Lopez's equation with an exponent of -1/4. Due to the strong nonlinearity of Lopez's relationships, it may not appear practical to coat large surfaces by manipulating gravity. Nonetheless, with an appropriate increase in the volume of the coating material, there is a linear scaling between area and time. To measure the spreading of puddles under standard gravity, we use the camera to monitor the spreading of puddles on sheets of polyester. Through centrifugation, we applied high gravity normal to the sheets of polyester and spreading puddles. Under 600 Gs, we decreased the capillary length from 1.5 millimeters under standard gravity by a factor of nearly 25 to approximately 60 microns. To achieve uniformly distributed high gravity, we first floated a flexible substrate and liquid droplet on a high-density fluid in a trough or petri dish. As the centrifuge spun up to a set speed of 2000 RPMs, the bucket tilted and went nearly horizontal as shown. The surface of the high-density fluid conformed to a cylindrical radius of curvature, which permitted uniform application of high gravity to the spreading puddle and flexible substrate. The trough held the high-density fluid, substrate, and coating droplet. The plate went in the holder of a swinging bucket, which spun in the centrifuge. We then took images of puddles after centrifugation using collimated LEDs transmitting light through the backside of the samples and into a camera. We also used a custom MATLAB script included in the supplementary material of the paper to measure the sizes of the coated areas. These images show a puddle of 80 microliters spreading under a standard gravity of 1 gram without centrifugation. The repeated measurements of spreading puddles with a radius greater than 5 times the capillary length showed agreement with Lopez's relationships. The thickness decreased proportional to t to the -1/4, and the radius increased proportional to t to the 1/8. These images show a puddle of 8 microliters spreading under a standard gravity of 1 G without centrifugation. These images show the progressive spreading puddles of 8 microliters under the influence of 600 Gs of high gravity. The repeated measurements of spreading puddles under 1 G with a radius less than 3 times the capillary length did not agree well with Lopez's relationships, which suggests the spreading occurred in an intermediate range between the surface tension-driven and gravity-driven regimes of spreading. In contrast, the 8 microliter puddles under 600 G showed a closer agreement with Lopez's relationships and exhibited a faster rate of spreading. If we were to extrapolate Lopez's relationships for the spreading of our 8 microliter drops under 1 G to the thickness associated with 1 minute of spreading under 600 Gs, the time required under 1 G would be approximately 12 hours. With these results, we believe the techniques outlined in this work might have potential as a new coating method with minimal waste. To conclude, this work appears to be the first to measure the spreading of droplets or puddles under high gravity. We suggest a mechanical approach of using high gravity to decrease the capillary length. Uniform gravity applied normal to a flexible substrate is possible by floating the substrate on a high-density liquid. Scientifically, we hope that this process might also be a tool for exploring the transition between surface tension and gravity-driven regimes of spreading. And finally, the outlined methods might have potential as a coating process with minimal waste.